Record. Okay, we're good to go. So it is Tuesday, March 9th. I had a pre-lecture and a reading. The lab for pre-lab is actually due on Friday. Let me fix that again. Is due on Friday. I moved the homework that was due, I think today. It is now due next week. I just updated the submission link and the name of the homework assignment, but I didn't change the actual assignment. And that'll give us time. Once we cover the 04 slides, we should be ready to do that. Because there was stuff of the problem one was like a diff amp, and you guys have never seen that before except for DC analysis. So I pushed it back again. And it won't affect anything else because we'll catch up during pseudo spring break, which is next week. Which means there is no lab next week. There is a lab this week. Your pre-lab's due for lab 4, and we will draw the goal for week 1 is to draw the cross sections. And I think I've got all the slides posted this time. There's the key PDF. There's probably about 20 PDFs in your lab 4 folder. The one that's important for the lab 4 week 1 is the one that is cross sections that ends in an S, not cross section or any of the other cross section ones. Is pseudo spring break for every class? It's just for my classes. It's because when I wrote the schedules, I was assuming spring break existed. So that's why there's no lab schedule. Yeah, everyone should have at least a pseudo spring break. What else is coming up? The next exam is Thursday, March 25th. And we'll be working on lab 4 for the rest of the semester. If you want to, you can actually double dip on your bachelor's and master's degree. You have to formally apply into the program, but 6 hours of your senior electives will count towards both your bachelor's and master's degrees. You need a good GPA, and it changes every year, so I don't know what it is. You don't have to take the GRE. You can see your advisors or contact Slava for details. If you email me, I'll give you Slava's email addresses. I don't know, I can't even pronounce his name. Begins with a B, and his last name begins with an F. For exam 2, if you have the 6th edition, it's chapters 5, 7, and 8. If you have the 7th edition, it's chapters 5, 8, and 9. And I believe the 8th edition is the same on those chapters. We will have the exam review. It's going to cover the last set of slides. The 03 slides is probably half of it, and the 04 and the 05 slides are a little bit shorter. You can bring in 2 sheets of notes. Don't worry about getting things signed. That's gone away with COVID. But just two sheets of notes. Your old note sheet would be helpful because there'll be a lot of material that we covered for exam 1. This is very cumulative. And what we're going to cover is the small signal stuff we've talked about already, calculating the DC operating point, the big ID, the big VGS, and the big V out, using those to calculate GM and RO, and then using those to calculate the voltage gain, the input resistance, and the output resistance. Now, everything we've looked at so far has resistors in it, which is great if you're building something on a board. Doesn't work so well once you
hear something toxic.
What? Okay, doesn't work so well. Probably the comment wasn't directed to me. Okay, doesn't work so well when you move into the IC world. So we're going to look at like the basic gain cell and how we're going to modify that for an integrated circuit. That's where we start out today. Yeah, with the basic gain cell. And then we'll look at the cascode and different biasing conditions. So here's the basic gain cell. Now this is a common source amplifier. The input's on the gate and the output's on the drain, so it's a common source. Instead of putting a resistor in, we've replaced the resistor to VDD with a current source. Now we can kind of do that because what is the resistor doing? It's setting the current for the amplifier and it's dropping some voltage. And that's what current sources do. One key thing to remember about current sources is an ideal current source, and I see people do, an ideal current source. It will drop whatever voltage it needs to maintain the current. So drop any voltage to maintain current. If it can't drop that voltage, then what happens is it collapses and it stops working. So the voltage here, if this is VDD, if this is 1.2 volts, this is probably not 1.2 volts. I can't say anything about that voltage other than it will be the voltage that the rest of the circuit needs to maintain that current. Another thing about ideal current sources is they're usually modeled like this, current sources. If you do a simple model of them, you can do something like this. And that resistance is 0. Because we don't want to lose any voltage across there. I may take my words back on that one in a minute. Okay, yeah. Inside an integrated circuit, you cannot build resistors. They're big. I got a picture here to show you how big they are. You can see them. And some of these may look familiar to you. Where is it? Right? Oh, there it is right there. The way I build resistors is I build really long, high resistive lines, and I call that a resistor. So they look like this. They take up visible amounts of space. We're using the same relatively expensive manufacturing process for every single one of our devices, and the cost of the devices depend upon the area. I can make transistors really small, down to the 5 nanometer, 3 nanometer range. Capacitors, I can build a couple of picofarads in like a micrometer size, not too bad. But I use capacitors in analog circuits a lot. And there's ways that analog techniques that people have learned where you basically replace the resistors with capacitors that are switched on and off. So they work. Where? 5 millimeters. Yeah, that says 5 millimeters. So you can see that. That's half a centimeter, a quarter of an inch. That one little branch right there. So this is about 1 inch across. Let's see. Oh, Alex is here. Okay, so everybody's here. So yeah, they're actually, you can actually physically see them. And you've probably seen that in those little tags they stick on things at the store. Things like that. Those little resistor, yeah, it's basically to set off an alarm. What? Yeah. I've never put a resistor on an integrated circuit. We built an ADC, we use caps. The dimensions for the ICs have been shrinking. 1960s, 10 micrometers. 2000, they got down to 0.18 micrometers. I remember the excitement. I was at ASU. I want to say it was like 1990, 1991. First sub-micron transistor. The things we get excited about. Now we're talking about 3 to 5 nanometers and shrinking. DRAM, the last time I talked to people at Micron, was down to 9 nanometers. So having these really big devices on there is expensive. Another trend that's been going on is logic circuits. For a long time were at 5 volts. And even the early ones were like +5, -12 of all things. As the dimensions went down, we had to lower the power dissipation because the smaller transistors were dissipating too much power they were starting to melt the chip. And we know, sorry, my throat sounds horrible. It's the dust and all the wind and stuff out there. The power dissipated is roughly equal to FC VDD squared. So for faster chips, the power dissipation is going up. If I can lower VDD, I can lower the power dissipation by a factor of VDD squared. So that was the motivation for this. And also the smaller transistors had lower threshold voltages, so we could actually operate them at lower voltages. And now we're down to 0.08 or so. Level of integration, 1947, there was only one transistor. It's not single transistors, there was one in existence. There was a one transistor circuit somewhere in New Jersey. In 1960, Jack Kilby at Texas Instruments developed the first integrated circuit. And Gordon Moore, one of the founders of Intel, came up with this idea that the number of transistors on a chip is going to double every 1.5 to 2 years. And it's an amazing prediction because it's actually come true. Now we're kind of pushing that limit when we get down to atomic scale transistors, but they're doing things that are making it like virtually true, like stacking silicon wafers on top of silicon wafers. So you're still getting more transistors per millimeter square. Yeah, now we have hundreds of millions and billions of transistors all on one chip. So this is the basic gain cell. And we know we can't use a resistor where that current source is. The area is too big, the gain is too low, and we'll talk about why. We'll talk about that in a minute when we get to the output resistance problem. Instead, I'm going to replace it with a current source load. The ideal output resistance of a current source is infinity. It's in parallel. It's got to be in parallel. That's true. And this is what, okay, don't make me do that, right? Okay, so the first thing we want to do is, this is a common source amplifier. We're looking into the gate, so the input resistance is infinity. The output resistance here is going to be the resistance looking into the drain of the transistor, RD M1, in parallel with the resistance looking up, whatever the resistance is of the current source. If it's an ideal current source, that's infinity. So that's basically going to equal the RD on M1. And looking into the drain of the transistor with nothing tied to the source, that will equal the little RO of transistor 1. The gain for a common source, and we've already derived this, is GM times big RO, and it's negative. So this is going to be negative GM RO1. Now, just from the argument I've given you so far, you can kind of get the idea. If the resistance looking into that current source was not infinity, it would severely degrade the gain. Let's say it was one of the resistor. If we'd replace that with a 2K ohm resistor, the RO of a transistor is usually like hundreds of K ohms. When I do this calculation and put the 2K ohms in parallel with the RO of M1, I'm going to get a number less than 2K. And my gain is shot. My gain is GM big RO. So putting something in there that has a higher output resistance where the current source is will make our gain significantly higher. And that's the goal of this. We've talked about this before. If we want to calculate RO for a transistor, the first equation I ever gave you for that was 1 over lambda ID. Lambda was in per volts, and we calculated that. Then you realized a lot of the Sedgwick-Smith problems give you the early voltage. So the early voltage VA is just 1 over lambda. And the way people measure it is they look at these transistor curves and they find the intercept, and they just draw this line out for all these curves and find the common x-intercept of those points, and that is the early voltage. And it's dependent mainly on the length of the transistors. So to process size this so that I get a number that's good for the whole process is they came up with this VA prime. And VA prime is the technology dependent component of that. VA just basically equals VA prime times the length of the transistor. And if you have to guess what the length is, what you always guess is the minimum length, because there's very few reasons to make the length bigger than the minimum length. VA is in volts. VA prime is usually given in volts per micrometer. So if I want to increase RO, it looks like I can make the process better by making lambdas, making VA bigger, making lambdas smaller, or I can mess around with ID. If I make ID smaller, I could make RO bigger. There are other ways, other tricks that we will learn today through the magic of resistance multipliers.
So in other words, if you want to increase that output resistance, you need to shrink the dimensions of your resistor.
Yeah, you'd want to shrink the L, but you're already at minimum L, so that doesn't help you.
I was going to say, wait, you want to shrink the L to increase resistance?
Yeah, oh yeah, you can make L bigger to make the output resistance. Yeah, you're right. It goes that way. Okay. But nobody ever wants to make L bigger. When we calculated GM, and this will be a good thing to know for the exam, is all the various formulas for GM. There's a couple of ways we can calculate it. We can use Kn times V over voltage, 2ID over V over voltage, and all the rest of this. When we calculate RO, it's VA over ID. So we take the voltage gain and say the magnitude of that is GMRO. And for most of these, for the cascode, for the common source, and the diff amp, the gain comes out to be GMRO. I plug that in, I do some algebraic reduction, and this is the voltage gain. So if you want to increase if you want to increase the voltage gain, better transistor, VA prime, Kn prime, a better process. VA prime's a better process too. I can increase the area of the transistor. So I make the W times L bigger, or I can decrease the ID. Those are the two things I can generally do. Not a whole lot. Notice the gain is higher. This is ID. The gain is higher. It's the highest in the sub-threshold region, but the transistor doesn't really work there. When I start going into saturation right here, the gain is always higher at the lower values of ID. Okay. Remember this chart. I cannot emphasize how important this chart is. Almost every single problem on the exam, on exam 2, will ask you to calculate, they'll either a DC operating point or something like that, will ask you to calculate gain, input resistance, and output resistance. This is the key to getting the output resistance right, which is the key to getting the gain right. If you're looking into the drain of a transistor, and this is the more general form, this is kind of like, this is sort of useless most of the time. If I'm looking into the drain of a transistor, the resistance I see is the RO of that transistor times 1 plus GMRS. So if I have an RS on there, and GMRS is going to be much bigger than 1, I can actually multiply the output resistance of that transistor by a number bigger than 1 and make it huge. There's one problem I put on an exam too a couple of times where I put this circuit on there, and it was me being cute. And the output resistance is like a peta-ohm or something like that. Just by multiplying and multiplying again, and you know, you get the idea. Looking into the gate, I always see an infinite resistance because there's no current. And looking into the source, I see 1 over the GM of that transistor times 1 plus whatever resistance I have on the drain over RO. And that usually comes out to be approximately 1 over GM. Not a great improvement there. Oh, I will get to that. The best you can do is you can get the voltage gain equal to the GMRO. And all this is going to do is decrease it, whatever its resistance is. Oops. Okay, so what we're going to do here is we're going to look at this circuit. I've replaced the current source. I've replaced that small resistor with another transistor, M2. Now this is still M1 is my actual gain transistor. It's a common source amplifier. Signals going from VN to Vout through this path right here. M2 is a current source. It doesn't affect the gain. It's basically acting like the current source, except that it will affect the value of big RO. If we're looking at this, the input resistance is the resistance looking in right there. It's still infinity. The RO, let's just change colors. The RO is going to be the, I have a resistance looking in here and a resistance looking in here. So RO is going to be the input resistance looking into the drain of M2 in parallel with the resistance looking into the drain of M1. Because from the output's point of view right here, there's 2 possible paths for current to flow. So it's going to be a parallel combination, and it's going to be smaller than what I originally had. Now the RN looking into the drain of M2, we're looking into the drain of a transistor, so it's going to be RO2 times 1 plus GM-RS. There's no resistance on the source, so that just becomes RO2. Looking into the drain of M1, I'm again seeing RO times 1 plus GM-RS. No resistance in the source, so this is just RO1. If you match those transistors to have the same output resistance, which is about the best you can do, what you've got now is your RO is about half of the 2. Yeah, the best you can do is make RO2 equal to RO1, and then your output resistance is going to equal half of RO2 or RO1. So that my RO is RO1 in parallel with RO2, smaller number than just RO1, and my voltage gain is minus GM big RO. Still better than what you were getting with the single resistor on the board, but not as good as I could have gotten if I had an ideal current source there. Now, as far as A0 and I don't, it's just absolute value.
Quick question.
Okay.
What does the gain CS mean? Is that the current source came from the current source, or
The gain CS, where does it? For M. Gain of the common source amplifier.
Oh, right.
Okay. Not current source, it's common source.
And for the output resistance, that's R in.
That says RN, or it's the R looking into the drain of M2
Oh,
is what I was meaning to write down. So R looking into the drain of M2 in parallel with R looking into the drain of M1.
and that's just equal to R output to.
Yeah. Right, because I have no resistances in the source of either M2 or M1. Okay. So this looks like a circuit I've put on the exam before, but well, basically, in order to have this thing working, we've got to have, what's going on here? Let me see if I can describe this without going into all the math and explain what's really going on here. You need all the transistors in saturation, not just one of them. When you're in region 1, let's see, which one do I care about here? Q3. Q3 is always in saturation because it's being forced into saturation with this current source. So it's always in saturation unless something goes horribly wrong. In region 2, I've got this transistor and triode. It doesn't have enough current to kick on yet and go into saturation, and this one is in saturation. And then when I go into region 3, where I actually have slope, and I have something that looks like gain, I'm putting all 3 transistors into saturation. So when you're dealing with that saturation check, you not only have to deal with, is my gain transistor in saturation, but are the current source transistors in saturation too? Any one of those going wrong is enough to make your circuit not work. Okay, yes, that's what I meant to say with this. Yeah. So we're looking at this circuit, and we want to figure out, okay, so RO1 is the output resistance of transistor 1, which is right here. It is going to be, what are we given? We're given BA, it's an NMOS. So we want to use BAN prime times its length over ID. For RO2, notice the arrow's going in the wrong direction, and they usually do this. It's kind of like CMOS. In order to turn this transistor on, we're going to put a PMOS transistor up there. So RO2 is a PMOS. So when you're calculating its RO, it's BAP prime L over ID. They may have, if you have an intelligent designer, they may have different W over L's. They probably have the same L. Well, it just, whoever wrote the textbook. Whoever wrote the textbook is probably a professor who's never actually worked before. Says the real, okay, so RO1, we want to calculate it. Let's go through this because this is going to end up being a little bit more tricky than you think. VAN prime is 22 volts per micrometer. And the length of that transistor is 5 lambda. So 5. And then I have to go back to the data sheet and look up lambda. It's not the same lambda as 1 over lambda ID. This is a lambda, and this has units of per volt. This lambda here has units of micrometers. or nanometers or whatever it is. So I have to take that and multiply by 0.09 micrometer. Well, that was in volts per micrometer, so I don't need the micrometer in there again. And just make sure you double check your units. And my ID was 20 micrograms. That one needs a micro because it doesn't have anything to cancel it out. Number 6, RO1, 495 k ohms. Much bigger than that 2 k ohms we were talking about before. RO2 is a PMOS transistor. So it's got a different, notice VAP is significantly smaller. The transconductance is also significantly smaller, but the size is the same, which is going to make our RO2 come out to be, I'm not going to plug the numbers in this time, 337.5 k ohms. So if I want to find RO here, it's going to be the RO of Q2 in parallel with the RO of Q1. Big RO equals RO1 in parallel with RO2. And that would be 200 k ohms. 100.7 k ohms when I put those two in parallel. So my actual gain, AV0, is going to be negative. The gain transistor is the one down here. It's the NMOS transistor. The inputs on the gate of that, the outputs on the drain of that. So it's my voltage gain is going to be GM of 1. This is where if you don't put the subscripts on the transistor, you're going to go batty thing when you go back and go. If I just wrote down GM, then the next thing is it GM1, GM2, or GM3, and I have to rethink this all over again. Write them down. It will save you some time. Times big RO. And we've got a value for GM1. It's 283 microamps per volt. And so my voltage gain comes out to be negative 56.8. That has units of volts per volt or dimensionless. Now I want to figure out what that is in dB. And remember dB, and this is a voltage gain, so I put a 20 out front, 20 log of the voltage gain. And it's actually the magnitude of the voltage gain. And you'll discover why that's important the first time you try to put in 20 log of negative 56.8 into your calculator and you get an error. You have to deal with the magnitude of the gain. You can't take the log of negative numbers. So I plug this into this formula and I get AV and dB. And this is the way most designers talk about gain. They talk about it in dB because then they don't have to multiply. They can just add their gains together through the magic of logarithms. I think that would be a great IEEE meeting. We all learn how to use slide rules. Okay, so this is the basic gain cell. Now, what if I want to make the gain higher? I can make the output resistance higher through the magic of adding a second. I'm going to add some resistance down here. So I add some resistance down here, and then I can multiply the output resistance. So this is the idea behind the cascode, the super high gain stage. It's called the cascode. That is not misspelled. It's not the Cascades. I don't know where this came from. I think it had to do with whatchamacallit, the vacuum tube terminology. No, it says, yes, Mr. Cascode. This is how I lose my phone. I have to carry it around with me because I can't log onto a computer without my phone. We want to increase RO to increase the gain. And I can't change the process. Generally not a good idea to make the current too small because I think things get noisier. And making L bigger is not always the thing to do. Yeah, this is the key right here. I put a resistance in the source of my gains, my common source gain stage, and I get to multiply the RO of this transistor by 1 plus GMRS, which is a number much bigger than 1. So if I can increase the output resistance, I can increase the gain. Okay, I really want to emphasize this right here because I see people doing this and sometimes they just scratch this out and say don't do this. If I'm looking into the series combination of 2 resistors and I want to find the equivalent resistance, it's just R1 plus R2. That doesn't work with transistors. Because there's other things, there's a dependent current source in there, there's a output resistance, there's all those things right here. Looking into the drain, my REQ2 of M1 is just going to be RO1. It is you can't read that, this one right here, RO times 1 plus GM RS. And there is no RS. Now, REQ3, when I'm looking into the drain of M2, does not equal RO1 plus RO2. It equals, I have to apply this formula right here. Looking into the drain, what I'm going to see is I'm going to see REQ3 equals RO of 2 times 1 plus GM2. And the resistance I see at the source now is RO1. It's a multiplier. And I can get really big output resistances this way. It's an amazing thing. And we'll talk about that. There's something I really want to say right now, but I saw it on a slide, so I keep putting it off. Okay, so this is the potato. Wait, I gotta find out where this is. Oh, there it is, it's slide 10, so I feel a little bit better now. We did that, we did that, we did this. Okay, so this is the famous potato. Now, even if I increase, oh, thank goodness, I in the wrong place. Okay, so it's not letting me do that. Draw with touch. Oh, great. Why is this doing this? Don't draw with touch. Draw with touch. There's some combination in here that will suddenly make me start being able to write again. I'm going to use my finger for now. My finger works fine. Oh wait, now I'm back to my stylus. Now my stylus works. Okay. I can make the REQ looking into a series combination of transistors really big by using the magic of resistance multiplication. But whatever this REQ is going to be in parallel with a potato. If the output resistance of the potato is low, this isn't going to help me because then I've got REQ in parallel with a potato and that equals a little less than a potato. Been doing this for a while, far too long. REQ, looking down as it's labeled on there, is RO of M1 times 1 plus GM1 times RO2. Yeah, and I can't put it in parallel with the potato. The voltage gain If the load equals infinity, if my potato is an infinitely large size potato, my voltage gain would be minus GM REQ, big RO. But that is, you got to always put it in parallel with the potato. Minus, I got the minus sign. Okay. We actually gonna finish this. We're behind. Okay. So the ideal thing to do would be to turn the potato into something where I can control the output resistance. So this is going to be in place of the potato. Oh, great. No, you're doing this again. Some points. I'm just gonna throw this thing. Okay. I love technology. There we go. Magic. It worked that time. What? I did not build this computer. Now, if I'm looking into the, if I'm replacing the potato, I'm going to replace it with 2 transistors so I can get the output resistance up. REQ looking into 1 is just going to be the RO of 4. REQ looking into 2 is going to be RO3 times 1 plus GM3 RO4. So I can make the potato's resistance equally big as my gain stage in order to keep the gain high. The purpose of the cascode is to have a really high gain. We'll talk about why that can be a bad thing too. I'm getting there. Run out of slides. Okay. So this is the idea. What we want to do is if we put 2 transistors, we put this cascode in there. Let's talk about let me talk about the cascode a little bit. My signal path here goes this way. That's my signal path right there. M1 is a common source amplifier. M2, the input is on the source, the output's on the drain. That's a common gate. And it's the common source, common gate combination that we call a cascode. Let's figure out, this is what I really wanted to say. Let's figure out the REQ looking down. So the REQ looking down, we've already done this quite a few times. Q on the NMOS side is going to be RO2 times 1 plus GM2 times RO1. I think you get pre-lecture quizzes that just kind of like take this to the extreme at some point. I don't know if you've had them yet or not. REQP, looking up, I see RO3 times 1 plus GM3 times RO4. And my total RO, the output resistance looking in from V out, big RO, is going to be REQ in parallel with REQP. So the advantages of this circuit is that I have a big RO. I have a really big gain because my gain is going to be GM big RO. Big RO, big gain. The disadvantage of this circuit is that I have a big RO. Now, why is that a disadvantage? Remember our basic model of the amplifier. I had something like this. I had RN. This is the first time I've ever done this, and I find this to be really fun. AV0 times VN. Now, if this gets to be really big, and I put a load on it, what happens? Unless the load resistance is bigger than RO, I don't get any power out to the load. So I can put this cascode stage into an amplifier to get a big gain, but I'm going to have to put some kind of buffer right next to it to make the big RO of my gain stage into a small RO. And what is that, like a common drain, right? So it's got the gain I want, but I can't drive anything with it. And the bigger I make RO, the worse the problem gets. Okay, and I've never pointed that out at this point before, so that's like brand new.
So it's just a matter of gain versus ability?
Gain versus ability, drive current, output drive current. So like if you had something like this, you had a stage like this, and let's say you wanted to drive a motor or an LED, something that has a, let's say this is like, we're just gonna call this, oh, not again. I just like push the buttons until it works. Can you see what I'm doing up there? My random button pushing, probably not. Let's see. At some point, okay. So I'm just going to talk about it for right now. If I made RL like something that was like a kiloohm, something that's driving milliamps, I can't drive milliamps out of this because my RO is going to be like mega ohms. And that will soothe me for a minute. I'll start pushing buttons again. Start fighting technology again. Okay, I want to make this even bigger. I want a bigger gain out of this. Now I definitely need my pen. Draw with touch. I can draw with my finger. And then I get this with that, and it doesn't do anything, so I turn that off, and I hit that with the stylus. And at some point, some random combination here makes this actually work. I'll just draw with my finger. If we're looking into this one right here, my RO, well, my RO down. Oh, and now I've got nothing. Oh, there it goes. Okay, so my RO, R down, my RD, it's going to be amazingly huge. It is going to be, looking in here, I see RO1. Looking in here, I see RO2 times 1 plus GM2 RO1. And looking where RD is, I have RO3 times 1 plus GM3 times the resistance looking down, which is RO2 times 1 plus GM2 RO1. Now instead of mega ohms, I've got giga ohms. Okay, does that do me any good? Because of the potato. The upward looking resistance is just RO4. And my RO, my total resistance, is R up in parallel with R down. So it's going to be a little bit less than R up. If I wanted to do this, I'd have to put 3 transistors into the potato to do it right. You got to keep the output resistance balanced between my current source transistors and my gain transistors. And I'm going to apologize in advance for the next slide, but I just still have to leave it in.
For the downward resistance, is that supposed to be RO3 at the very beginning?
Yes, it should be an RO3. And I can't write again. But there should be, for RD, there should be an RO3 in there. Maybe my stylus, you know, it could be that my stylus is going dead. Draw with touch. Can I put, that's RO3. My finger doesn't do that good of a job. Turn touch off. Ah, there it goes. RO3. Yeah, and I have put one of these on an exam before with like 5 transistors on there to get a pedal. Okay, apologize for the next slide in advance, but for some reason I'm actually hoping for Tequila Sunrise to happen this year. Don't drink at 6 o'clock in the morning. I can't think of anything that would make me sicker than.
What was the gain for that last?
The gain, oh yeah, I didn't write that down. The gain would be GMRO.
Oh.
Minus GMRO. And it would be, which GM would it be? There's 4 transistors in here.
It would just be small GM?
The small GM. It's the GM of transistor 1. It's the GM of the common source. The common gate doesn't have a lot of gain. And there's a proof of that, that the Cascode does have a gain of GM of the common source transistor times RO in the Cedar-Smith book, but I'm not going to do that. Just if you have to guess what any of these stages, it's GM RO. So chunking is what happens at Tequila Sunset. Although I have seen chunking happen in downtown Flagstaff at Tequila Sunrise. Yeah. No. And this is all going on YouTube. Yeah. Why did this all of a sudden get, I don't know. Let's make the notes smaller, that might help. There, okay. So this is a folded Cascode. And I think this shows up in somewhere in the homework or exam problems or things like that before. What have I done here? Let's go to my first line of defense, since I haven't looked at these slides yet. We still got 15 minutes. My input is right here, and my output is right there. So my signal path is going this way. That's where signal's going. So the other 2 transistors there by default are current sources. So M2 and M3 are some kind of current source active load type thing, which is kind of like the same thing. I'll just call them I sources for now. And M1 and M4 are providing gain. M1 is a common source. M4 is a common gate, so this is a Cascode. The combination we've just looked at. This would be M1. The common gate would be M4. And the other transistors are current source. I haven't even looked at this slide for like a whole semester, so I'm going to. If Vn goes up, VGS of M1 would go up. So ID would go up. ID1 would go up. The voltage at the drain of M1 equals the voltage at the drain of M3. Both of those things, if this voltage goes up and the current goes up, they're both going to go down. BD1 equals BD3, and they're both going to go down. And if this voltage goes down, ID4 is also going to go down, and I don't know how to, okay, ID4 goes down, and B out goes down. So this is an inverting configuration. Okay, let's see how far do I, let me just look ahead and see how far I want to go with this. Oh, this is a good thing to do. That's a good thing to do. Let's just do the next couple of slides and call it good. Okay. So I'm given some DC bias for this. I've got ID3 is 100 microamps. So I'm going to draw this on here. This looks like an old exam problem. ID2 is 50 microamps. I'll just show you what level of things people mess up on the exam. Okay. What is ID4? You've got an exam paper right in front of you, and one of the questions is, what is ID4? Since I've drawn these currents on the schematic, it's obvious. Taking the time to draw those currents on the schematic makes it a lot easier. I've got 50 microamps in 2. It's in series with M4, so they have to have the same current. ID4 is also going to be 50 microamps. Some people miss that. Now I've got a trick question. I want to figure out what ID1 is. What principle of circuit analysis can you use here? Thank you, Sean. KCL, Kirchhoff's current law. The gazintas equals the gazatas. What goes into the node, what goes into the node equals what goes out of the node. You didn't have 188 for me. Okay. And you hear old engineers saying that all the time. It's gazintas equals gazatas. Gazintas equals gazatas. What goes into the node equals what goes out of the node. Okay, it works with pipes too. The water that goes into the pipe has to come out somewhere. Okay, so I've got 100 microamp. Oh, great. I've got 100 microamps going in, 50 microamps going out. ID1 is 50 microamps. Okay, also, I just decided to crap out on me, sorry. $50 microamps. You can do that step. You're like halfway there. All the currents on the schematic are right there. Yes, that's a real exam problem. That's all I asked for. Okay, the next problem looks probably like one of your pre-lecture quiz problems. It's finding REQs. And finding these equivalent resistances is the key to figuring out the gains for all these. So we start with the simple one. The easiest one is REQ1 because it's looking into the drain of M1. So this is just RO1. I hate to do this to you at the end of the day. REQ5 is looking into the drain of M2. So REQ5 is RO2. RO2. REQ2 is looking into the drain of M3. So this is RO3. Okay, what else do we have that's relatively straightforward? Oh, let's do REQ3. Now we're looking into the source. So this is going to be the equation, if you can't read it, I just barely can. GM 1 plus RD over RO. That's into a source. So REQ3 is looking into the source of M4. So it's going to be 1 over GM4 times 1 plus something over the RO of 4. And whatever resistance I see on the drain, I'm looking into M2. So that would be RO2. Okay, so we got this one. REQ4. Dr. Brower. REQ4. REQ4 is looking into the drain of M4. So that is this equation for looking into the drain. RO4 times 1 plus GM4 times whatever resistance I see on the source. And at the source, I see the parallel combination of REQ2 and REQ1, which is RO3 in parallel with RO1.
And REQ3 was just equal to REQ2, right?
REQ, wait, REQ, where's REQ3? Yeah, REQ3 is right here.
Oh, okay.
We got REQ3, we got REQ4. What is my output resistance? My output resistance is looking into this node right here. So it's REQ4 in parallel with REQ5. And we're just going to write it like that. REQ4 in parallel with REQ5, which has a simple expression, in parallel with RO2. So if I wanted to figure out the output resistance of this, I'd have to go through and do the calculation on RO4, figure out what that is, put it in parallel with RO2, and I could get the gain. AVO, I gotta remember this has a minus sign. Yes, it does have a minus sign. Is minus GM, my common source transistor. Which one's my common source transistor? Is this one right here. That's where my input's coming from. So GM1 times big RO. You guys, output resistance yet out yet. Key skill we're getting here is figuring out what these output resistance is. Now there's a shortcut here. And okay. Let me just talk about that and then I'll let you guys go. If I look at this, if I have something that looks like this, and I almost want to do this. Oh, great. Let me just do this. Okay. And then I'm going to move you guys over here. Okay. If I have an expression that looks, like this, RO equals RO is 1 plus GM RO, let's just call it RO2. pretty much all the time, the GMRO2 is going to be much bigger than 1. So a good engineering approximation here is that RO approximately equals RO GM RO2. It's kind of a shortcut that you can use to avoid having these big, long expressions. And they use that in the book. And I do, if I recognize them, I mostly accept them on the exam. And if you catch me giving you points off for that, that's okay. It's a quick way of like just approximating what it is. You will be off by a number. It won't quite be the exact value. And where are we actually at? Yet another. Let's not start this one today. If we start that one today, then we're into IC biasing. Let's do this as a review of finding output resistance starting next class. Yeah, I think that's fair. Okay. Any questions about life, the universe, and everything? Anything? The CDC has now declared that they've actually done studies on huge scales of people who've been vaccinated, and they found that they actually did not know this before, is that if you've been vaccinated, you're highly unlikely to transmit the disease to anybody else. Even if you pick up like a mild, it just makes you much less likely. So you're not getting it from me.
So,
What?
Hey, Julie.
Yes. Okay. What?
So I got your email about the opening.
Yes.
I'm wondering if that's still open.
I don't know. I had a lot of people respond, and I'm having them send resumes by. So if you want to do it tonight. Send me an
Okay.
Who am I talking to? Chris Weber? Okay, yeah. I've had like 10
This is
people.
Chris.
Okay, Chris. I've had like 10 people
Yes.
respond already, so. And Eck is a little overwhelmed. But it's a good job. I would not mind working with the guy. He's very straightforward, but can be a little demanding. But he explains what he wants. So that's usually it's the people I have trouble working for are the people who just say like vague things like do this, and I don't know how you were supposed to do.
Sorry,
that.
who?
Eck, if you know him. Eck Dory. He's a CS professor, and he's in the 6th faculty. So if you go to the 6th faculty site, his email will be there. Send him a resume and let him know what you can do.
Can't say I do.
Okay. Okay. Is that it? Everybody's here, so I'm not worried about attendance. There's